Welcome to the second part of the SPI series. Today we will program with Zephyr the SPI. We will program our nRF developer kit with the nRF52840 and program or reading out the sensor data from a BME280. So it will be a little bit more complex, the programming, since we have to read out all the registers and so on. So first, a few reminder what we are doing. So we have our SPI controller and peripherals. The controller will be the nRF52840 developer kit and the peripherals the BME280. Here we have to connect the Pico line, the Poke line, the clock line and the chip select line. We're starting with a project, with a empty Blinky project. So just searching here Blinky and the basic project selected. I call it my SPI BME280. Create application. I'm using the toolchain 2.2 here. Yeah, you see already there. Then I make the build configuration. Oops, okay. Open it 3 times, yeah, okay. Choose our board and go on build configuration. When the build is done, the first question which arises is of course how we connect our BME with the nRF SDK. This we can look here in our Visual Studio. There we're finding the resources. When we're looking here, we will use SPI1. Yeah, and you're seeing here there are some MOSI, the clock line and the MISO line. So we have here the MOSI at GPIO 0, pin 30, the clock line at GPIO 0 and pin 31, and the MISO is at GPI 01 pin 8. Here is no chip select. We will make this manually. We can also let this make Zephyr, but I will explain it later why we are not using it or what's happened if we are using it. We can also look in the device tree, of course, if the SPI is there and active. We're seeing here SPI1 is okay. We are not using SPI0 because you see here cannot be used together with I2C0, and the status is not set okay because the I2C0 is in the Blinky activated. So, and you can see here also the pins which are defined. Yeah, we can go here directly and we're seeing the same pins here. GPIO 0 for the clock line and pin 31 and so on, like we saw it before. And the first thing what we have to do is, of course, in the project file we have to activate the SPI and have to set it to yes. In the next step, we take a look at the connection now. So you see here our schematics, how we connect it. We have here our BME280. Yes, the BMP280 is similar. The BME, I think the downer ones are exchanged. So you have to be careful. It depends also with which module you have. So we connect the power supply, of course, here with 3 volt and the ground, and the clock line here with P031, yeah? And the SDE, so the input from the BME, we are connecting to GPIO port 0 and pin 30, the green line, and then we're having the chip select, which we are connecting to GPIO 1 and the pin 7 I choose here. Yeah, we will implement it with an GPIO later. and the SDO, so the output from the BME, we're connecting with GPIO 1 and pin 8. You can also see here how I connect the developer board with the BME. I again connect a logic analyzer. This is the left pins. If you don't have one, no problem, but it's always good to check it later. And then what we are doing first is we read out the chip ID again. So the BME has a few registers, and when we take a look at the register table, we're having the register with the chip ID, so the register D0, and we have to get the result 60, like in the video before. The first thing what we have to do now is, of course, open the main file and adding the SPI header and also a few macros for the registers. I also already include here. So you're seeing here the SPI header and also the chip ID register D0. What we're needing for the starting to read out the chip ID register. Then we are needing two devices, an SPI node. So the SPI1 node, the device here, we're getting into this device is DT-get and the name from the SPI node. And the same is the GPIO 1, we're needing it for the chip select line, which we're putting on GPIO 1 at pin 7. And then we can directly build it for testing. We make a pristine build because we changed something in the project file. This downer part here we can delete. I mean, this is for the blink example, we don't need this. We make also this away. Sleep timer we let inside. So, and in the next step we're making the configuration for the SPI. How we want to use it. We use the frequency 125 kilohertz. So save it, that's the slowest one which I can set, at least what I found out. Then the operation mode, we are always writing and reading 8 bits, so setting it to 1 byte. And here you can also set like the clock polarity and the clock phase and so on. But since this is everything 0, we let it like this. It's not a slave. So this parameter we don't use at the moment. We can also set here a chip select, but then we have to define it first, and we make it manually, so we don't use this parameter here yet. In the next step, we read out a register, since we want to read out the chip ID. Here I've written a function for this. What's happening here is that it's a little bit more complicated here. We're needing actually, you see here I have read register. I put here the register value, so it's an UND8, so byte. And how many bytes I want to read out, it depends on which area I give to the function, and I have to also set the parameter from the size of the array. So this means how many bytes I want to read out. First, I have to make a write buffer, so a transceive buffer, where you need only 1 byte there only, and I save there the register what we want to read out. It's a little bit more complex. Normally it would be enough if we have just an array, like we had it in Arduino or something like this. Here's the structure. Actually, I don't know why they're making it a little more complicated. There is actually you can define more buffer in an array. And so you could here make another array that you can write more values at once, but we are not using it. We are just writing 1 byte here, and then later you have to put it in another set, so another variable where you put all the buffers here inside and writing how many buffers you are using. Since we are using only 1, you see here's only 1 inside. It's look like this. With receive buffer, it's actually the same. You have to set here the area. We are using only 1 area with a size which we give as parameter for the function, and put it also in a set from buffers. But we have only 1 buffer actually. In the next step, I have to set the GPIO device, the pin 7 to low, our chip select. Then I set the register. Actually, I did this already before. I don't know why I do it again. Can do it away here. So then I'm making an SPI write. And there I give the SPI device with our configuration and with our SPI transmit buffer set. If there's an error, we stop the do line. If not, we're making also after this the read. So this means first we are writing the register what we want to read out, and afterwards we're making a read. Remember, actually it's not different from writing and reading in SPI. It's just you're having a poke here and a pico line. We're needing a clock signal. We have here also a transmit function where you can make both parallel, so you can receive and write something parallel. Here this means with the write means the read is area with null, so no values inside, and with read opposites. This means the area for writing something is always null, so we don't get there anything. Afterwards, after we read out our registers, we're putting the chip signal at high again. If an error went, we are just saying it fails. And the next step, I think I forgot to initialize. No, it's everything right. I use the function read chip ID, so that I have an own function. For this, I just using here, actually I also don't need the error variable. I just read out the chip ID register and define here buffers. This is only 1 byte what we want to read out, and then I store it directly in structure for the BME280 data. I didn't define it yet. I will do this now. You see here the structure is a little bit longer because we have to store later a lot of variables. So I go up and define the structure. Here are the compensation parameters, calibration registers. Then we have using the uncompensated measurement values and the compensated measure value, and the T fine, which is when you calculate the pressure and humidity, you're needing this variable for the calculation. And here we have our chip ID, which is for the starting only relevant. And in the next step, we are just in the main. We are first initialize our GPIO, that is an output, and setting it to high. At the beginning, we're checking if our SPI device is ready, and afterwards we are reading out our chip ID. Let's compile and see if it's working or if I forgot something. Then I flash it at our board. And when it's finished, I connect with the virtual COM board. Make a reset because I don't make it in the while loop. You're seeing here I get the chip ID 60. Yeah? Let's also look at the logic analyzer. So I make reset. You see here is the transmission. What we had here, we're having here that we're sending the variable D0 and getting the answer 60. I mean, this was the easy part, yeah, now it's become a little bit complicated for the BME280. We see we're having here first the calibration registers, yeah. When you're looking here, we have 18 calibration registers which I have to store for the temperature calibration, for the pressure and the humidity. And the first ones are always 2 bytes, yeah. You have also to take care of the data type. Yeah, here's unsigned and here's signed, yeah, so that you don't mix it up. So humidity is the most complicated one because here is one which is not 2 bytes. There are sharings then also 1 byte. Yeah, so we have to read out this. And how we do this, we are always setting the first register from what we read out, and then we're reading out normally 2 bytes. Since the counter from the pointer, the register pointer always add 1 up, so we get afterwards directly, when we read out 88, we get 89. So for this I have already written another function which is called read calibration registers. Yeah, and what we are doing here is actually we are having a variable where we store the results, which has a size of 2, so 2 bytes. And you're seeing here the register addresses before we define, no, we didn't define it yet, so good that I take a look. So we copy it. So you're seeing here the starting register for the calibration register T1, T2, T3, and for the pressure and the humidity. And this is what we are doing when we read out the calibration registers. Yeah, then we directly combine this. This we shift 8 bits to the left, have to convert it to Win16. And the first bytes are the first 8-bit. Yes, then we're getting the T1, and the same is with the pressure, always starting with the register where it's stored, and reads then always out the register and storing in the variable. And with the humidity, like I said, here we have only 1. Yeah, we can take a look. So 1 byte which we read out here. So this is why I give here the size of 1. We can still use our array with a size of 2, it's not a problem. And a little bit more difficult is it then with H4 and A5. See here I have to shift it 4 to left, and I have to make the first bits here to 0, so that I get the right value. Yeah. When you're looking here again, H4, yeah, the 8 bits from the E4 register have to shift it 4 to the left, and from the E5 we need only 4. The first, the H5 register is similar to H4. Yeah, you're seeing here we're shifting again 1 from the register 4 to the left, and the other we are shifting 4 to the right. Let's see, so we are needing again the register E5, and from this only the bit 4, 5, 6 and 7, which we have to place on position 0, 1, 2, 3. This is here, we are shifting this to the right. Yeah, we don't have to make an AND before with F0 because the bits which we are not needing, they're anyway shifted away. Yeah, and the E6 we just have to shift 4 to the right. Then we're printing out all the calibration register. We bring this together in the main function. Yeah, I make a short sleep inside it, a delay for the logic analyzers, then I flash it directly. Also connect directly to the COM port. And here our register values. Yeah, with your sensor, when you're doing it also with the BMEs, they are not the same. Yes, they are always different for every sensor. So this wasn't the most complicated trial. It was already complicated, but the sensor is not so easy. So we have to read out or set first a few parameters. You're seeing here the memory map from the registers, and we have already the chip ID here, which is 60, which we read out. Now we're having to set the control register for humidity and the control measurement register. And why this is like this? First, when you're starting the sensor, it's starting in the sleep mode. And for changing the mode that it measures something, you have to set it, the first byte of the mode, to 11. The mode itself is then the control measurement register. So you're seeing here mode, these 2 bits we have to set. And the same is with the oversampling parameter. We're having here one for the temperature, one for the pressure, and one for, where is it, for the humidity. Here's this one. You have to set first the one for the humidity. If you let it to 0, 0, you get always the result 80 in hex code. Yeah, you see this. I think I have also, here you're seeing this. When it's 0, then we don't have any calculation. It's skipped and the output is always 80, 0, 0. Yeah, and we are setting it now to oversampling, 8 oversampling. So it makes 8 measurements and taking the middle value from this. And how we are doing this? So we are implementing like the read register function. We are implementing a write register, set register function, which working quite similar. We're having here our register and the value what we want to set. This is only 1 byte always, and the value, what you have to take care, we are not writing the register when it's a write command. We are using the register, but we're making the first bit of this register to 0 set the sensor knows it's a write command. And this is why we're making here an AND combination, yeah, is that the first bit from the register is then 0. And the second value what we are writing is then the value, of course, for the register. Then we are sending again, we are making again our buffer array, and with the length of the array before, and then our set. We are using always 1 array, so it's a little bit over much, but you know it already. Then we're setting chip select line to 0 again, then making a write command, and then we're making the chip select to 1 again. And in the main, we are just adding then the setting of the register. After the calibration. Yeah, don't forget the humidity you have to make first, and sensor register for the control measurement. And then the sensor already starting to measure something. Now we have to read out, of course, register values. The register values you see also from the memory map. We are having 8 bytes to read out. Yeah, we're having one for the pressure, 3 for the pressure, 3 for the temperature, and 2 for the humidity. And it's starting with F7, and then we are having here in the row. So I can make it at once, and I want to show to you how is the transmit function working in this case. For this, I'm defining here a function read sensor values. I mean, I could use also like the read register function that we had before and read every register single, yeah. But I want to show you how to make it in once, yeah. Writing, so a duplex writing and reading by our own. So we have to read then and write 9 times, so 9 clock cycles, because we have to set the register first, and the last time we're needing a clock signal to get the last register. So we're setting F7, F8, F9, FA, FB, so the register what we want to read out, and the last one just a dummy register. And then we make an array again, the buffer again with the buffer set, with the size, and we're making an array with the same length for receiving the value. And then it's, instead of writing and reading separate, we're making a transceive command. You're seeing here SPI transceive, and there we're giving both sets, the TX buffer set and the RX buffer set. And afterwards we are storing the values in the uncompensated pressure, uncompensated temperature, and uncompensated humidity. So I can write this now. We're making this in the while loop. Yeah, flash it. And you're seeing here we're getting the uncompensated values. In the last step, we have to calculate the compensated values. These are a little bit complicated functions. Take a look in the data sheet. Yeah, they are standing 100% in the data sheet. I copy it here. Yeah, you're seeing here one function for compensates temperature. Yeah, you're using the uncompensated values and the calibration register, similar with pressure, except that you're having here also from the temperature compensation inside the T fine, which we calculated here, and also the humidity. Yeah, you can take a look at the data sheet. Where these functions are defined. Here you're seeing the functions, yeah, you can normally just copy them here. Calculation function. After I put it inside, I'm just calculate the compensation. And flash it. And you're seeing here the temperature is 29 degrees. Yeah, when I put my finger there, it's a little bit getting up. So we're having here the pressure, 1007 Pascal, and the humidity is 100%. we are in raining season here. I mean, for sure it's not 100%, but 99%, so it's correct. And when you take a look again at our finite state machine, yeah, so we read out the chip ID first, the 1 byte, then we're reading out the calibration register, then we're setting the control humidity register, the control measurement register, reading out the sensor values, then compensate the sensor values and going in a circle, yeah. And you can also check it here when we are making now with the logic analyzer, and you're seeing here that really in this time we're reading out at once, so we are sending and receiving at the same time something, yeah. This was the difference in this when we're making transceive instead of read-write. We can also let Zephyr automatically control the chip select pin. For this we have to define in an overlay file in the device tree the pin. So I create an overlay file and defining SPI1, the chip select GPIO with GPIO1, pin 7, chip active low, and device here with the label A. This I can then use here up, so I have there to define also a structure first, get it from the device tree. So we get a GPIO specification from the device tree, yes, here is GPIO with the label A, and then save it in a GPS chip select control structure and then use it here. And what we have now to do, of course, we have to uncomment also GPIO the manual control of the GPIO pin. So yeah. Yeah, and the last one I think is here, so initialization, making it as output. Then we're making a pristine build because we changed something in the device tree. When this is done, we flash it to our device. And when we open then our virtual port, I reset it, so that you're seeing we're getting strange value already here, and then we do not even get the chip ID. And this has a reason. Yeah, let's look at the logic analyzer. Did he catch all? No, not. Okay, again. So here at the beginning. What was it? Here you're seeing already the problem or the difference. The chip select line goes after a write, then directly on high again, so it deactivates the device and then activate it with a read again. And when you're seeing here, you don't see it because the first bit is also a 0 from the answer when we're going to the next. At this line, you're seeing here's the register from the calibration register, we're having here's the 88, and afterwards the device already wants to answer the BME, yeah, setting the POKI line on high, but then the device gets deactivated and then it's going to 0 again. And so we're getting wrong values, so we're getting only the second byte, so we're getting strange values. Where it's working still okay with our programming is when we read out the registers from our temperature, pressure and humidity because we are using the transceive function here, and you're seeing that we are sending all the time F7, F8 and so on, and the chip signal is with the transceive all the time low when we're making it in one row. So for this we would have to use always the transceive function and not the read-write when we want to read directly something out. So have to be careful a little bit. It's always good to having a logic analyzer to see this, and sometimes better to control it by yourself, so that you know what's happening. This was an introduction to SPI and Zephyr, a little bit more detailed here because the sensor is quite complex to control, and you saw also that it's sometimes not so easy to control such a sensor and sending the right commands. So the BMP280, BME280 and BME680, they're working quite similar. So if you understand this sensor, you will also understand the other ones. And with I2C, it's working actually quite similar, except you have to exchange the data lines, and you don't have to change the register address for a write command. I hope it was understandable for you and you could learn a little bit, and if you like the video, give it a thumb up, and see you in the next video.